Good evening, everyone. In the last lecture, we discussed about the electrostatic potential, and we also discussed about the equipotential surfaces. And we discussed about the different properties of the equipotential surface, right? Here we discussed that work done on the surface of an equipotential surface. From one point to another point is always zero, and electrostatic field lines are always perpendicular to the equipotential surface, right? And each and every point on the equipotential surface has the same potential, right? But today we'll be doing some problems related to some standard questions related to electrostatic potential calculation, right? So let's begin with the first question here. That's we have to calculate the electrostatic potential due to charged ring, right? Due to charged ring. So first, we'll be calculating the electrostatic potential at the center of a ring, and then we'll proceed further to calculate the electrostatic potential on the axis of a ring, right? So let's discuss about the potential at the center of ring, right? So let's suppose that this in this figure you can see that we have a ring of radius r, and there is a charge q which is uniformly distributed on on this ring, right? It's uniformly distributed, and q is the total charge on this ring, and r is the radius, right? Let's suppose that if I take an element of charge on this ring, right? If the element of charge on this ring is suppose dq, right, of length dx, right? So dx is the length of this charge element, and dq is the charge on this element. And if we calculate the potential due to this elemental charge at the center of this ring, it will be the potential due to a point charge. And we know that potential due to the point charge is nothing that's equal to k dq upon r, right? K dq upon r. So distance from the center to this elemental charge dq is capital R. So we'll be writing it as k dq upon capital R. So it will be a very small potential. That's why we write it as dv. So dv is equal to k dq upon r. That will be the potential due to this elemental charge, right? So now in order to calculate the total potential at the center of this ring, we will integrate this whole ring, right? Over this circumference, right? And then we'll get to know about the total potential, right? So if we integrate it on both sides, so k and r is a constant, so this k and r will come out of this integral, so it will be integral of dq. And integral of dq is nothing, it will give us the total charge of this ring, right? So it means that if we integrate this dq, we'll get to know about the total charge of this ring, and the total charge of this ring is nothing, that's given as capital Q. So integral dq will be replaced by with charge q. So it means our potential will be integral of dv, that will be v, right? So it will be equal to kq upon r, right? So it means that the potential at the center of the ring, that's vc, will be equal to kq upon r. So this is the potential at the center of this ring, right? So kq upon r will be the potential at the center of the ring. Let's move on to the next part of this ring. The next part is that we have to calculate the same potential, but now on the axis, right? On its axis. And you can see in this diagram, there's a point P on the axis of ring, which is at a distance of x from the center of this ring, and the radius of this ring is once again r, and the total charge on this ring is once again q, right? So what we'll be doing is that I'm selecting this dq charge, right? dq charge, and I will try to find the potential due to this dq charge at this point P, and then we'll calculate it. We will integrate it over the whole ring to calculate the total potential due to this charge plus q at this point P, right? So the potential here will be due to this dq charge, that's dv, that will be k dq over distance, right? Over distance. And you can see that k dq upon r, small r, will be the distance from this dq charge to this point P, right? And we can see that if this distance from here to here is x, and this distance from here to here is the radius, right? This is the radius, and this will be the hypotenuse. And the hypotenuse will be equal to nothing, that will be r equal to root of r square plus x square, right? That will be under root of r square plus x square. So now we can replace this r here with k dq, and r will be replaced here with under root of r square plus x square, right? R square plus x square. So this will be the small potential due to this dq charge at this point P, which is placed on the axis of this ring, right? So in order to calculate the total potential now, and you can see that if you take any elemental charge dq on this ring, right, and all those elemental dq charge will be at a same distance, right? That's under root of r square plus x square, or you can say this term here is under root r square plus x square is will be a constant for all the elemental rings, right? All the elemental charges here. So it means that we have to integrate it over the complete ring. So that will give us the total potential on the axis of this ring. So we'll integrate it on both sides. That's k dq over under root of r square plus x square, right? Now once again, k upon under root of r square plus x square will be outside, right? So it will be left with integral of dq, right? Integral of dq. So integral of dv will be equal to, that will be equal to k upon under root of r square plus x square. And this integral of dq will give us the total charge on this ring, and the total charge on this ring is plus q. So it will be nothing, that will be equal to q, right? So it means that the total potential at the point P due to whole ring on its axis will be kq upon under root of r square plus x square, right? So integral dv will be v. So on axis, v axis will be nothing, kq upon under root of r square plus x square, right? So this will be the total potential at this point P on the axis of this ring, that is kq over under root of r square plus x square. And on the center we calculated as, you can just calculate on the center as well from this equation. If we put the value of x here equal to 0, the value of x is put here equal to 0, it means that the potential will be the potential at the center of this ring, that will be kq over under root of r square, that's r. So kq over r, right? So you can confirm from here also that at center the potential due to this ring will be kq upon r, right? Now let's move on to the next let's move on to this question, very small question here, right? With respect to the ring, with respect to the potential of this ring, right? The question is that find speed of the charged particle when it reaches at center of the ring from point P on the axis as shown, right? So there is charge minus q here. There's a charge minus q here at point P. The mass of this minus q charge is m, and it is released at this point. When we say the particle has been released at this point, means we do not give any initial speed to this particle, or we can say that the initial speed of this particle here is 0, right? So u will be 0 at this point P, and we are releasing it, and you can see that this is a positively charged ring, and because of this positively charged ring, the electric field on the axis is always away from the center, right? It's along the axis, away from the center, right? So because of this positively charged ring, the electric field vector will be in this direction, that's our E vector, right? And there is a negative charge placed here. It means that this negative charge will be attracted towards the ring, right? It will try to move, it will move towards the center of this ring through the point O. So the question says that we have to calculate the speed when this charge is going to reach this point O, or the center of the ring, right? And one more important point is that, you know, that electrostatic field, it's a conservative field, or we can say the total energy is conserved here. Now at this point P, there will be potential energy for this charge and kinetic energy as well. And since it's initially at rest, so we can say that initial kinetic energy for this charge at point P is equal to 0, right? And the initial potential energy Ui at this point P will be equal to, that will be at this point, you can see at this point the potential due to this ring at this point, let's suppose that's v p and multiplied by this charge minus q, right? That will be the potential energy of this charge minus q, right? Since this charge is placed at a distance of x equal to root 3, so the potential due to this ring at this position will be kq over under root of r square plus x square, that will be equal to kq over under root of r square plus root 3 r whole square, right? Correct. So it will be nothing, vp will be equal to kq over 2r, right? Kq over 2r. So this is the potential at this point. If potential at this point is kq over 2r, it means that this minus q charge will have a potential energy, initial potential energy at point P equal to minus K capital Q small q over 2r. So this will be the initial potential energy for this minus q charge, right? Now, once this charge reaches this center O, right, it will be having some kinetic energy, final kinetic energy. It will be having some final speed. Let's suppose that the final speed of this minus q charge when it reaches this point O, let's suppose that is V, right? Let's suppose that is V. So the final kinetic energy will be equal to half mv square, right? And the final potential energy will be equal to the potential due to ring at point O multiplied by this charge minus Q, and potential at the center of the ring multiplied by this charge minus Q will be the potential energy for this ring and charge system at this point, right? So potential at the center is KQ over R, right? Multiplied by this minus Q will give us the potential energy at this point, right? So now let's apply the law of conservation of energy. So the total mechanical energy will be conserved here, right? So we can use initial kinetic energy plus initial kinetic energy plus, just a minute. So the initial kinetic energy plus initial potential energy, that will be equal to final kinetic energy, right? Plus final potential energy, right? You find, right? And we can use this here. So initial kinetic energy is nothing, that's zero, right? And initial potential energy at this point is equal to minus kqqq over 2r. We can write it here as minus kq over 2r, right? That will be equal to final kinetic energy, that's half mv square, right? And the final potential energy, that's minus kq q over r, right? And from here we can see that it will be equal to kq over kq q over 2r. That will be equal to half mv square, right? Half mv square. And from here we can calculate the v, value of v. 2 and 2 will get cancelled. So v will be equal to under root of k capital Q small q over m, right, into r, right? So this will be the final speed at this point O. At this point O, due to the force of attraction because of this ring, right? So this will be the final speed, right? So let's move on to the next concept here. Now we have to calculate the electrostatic potential due to a charged non-conducting ring, right? We have to calculate the electrostatic potential due to a charged non-conducting ring. Non-conducting sphere, right? Now, there will be two cases for the non-conducting sphere as well. One case will be for the point outside the sphere, we have to calculate the potential, and also for the point inside the sphere, we will have to calculate the potential, right? So we'll be doing both the cases one by one. Let's start with the case number one. Let's suppose there's a point here, point P. Let me call this as point P. That's outside the sphere, right? Outside the sphere. Since this is a non-conducting sphere, and for non-conducting sphere, the electric field inside is not equal to zero, right? The electric field inside the conductor is not equal to zero. You can just mention here E inside is not equal to zero here, right? So E inside is not equal to zero for a non-conducting sphere, right? So this is a point P outside this sphere at a distance of small r, right? And the radius of this sphere is capital R. We have to calculate the potential outside this sphere, right? So we know that dV is dV over dr, that's minus dV over dr, that's nothing. That will give us the electric field, right? That's equal to the electric field, magnitude of the electric field. Or we can write here dV will be nothing, that will be equal to minus integral of ADR, right? ADR, right? And where to find the potential? Potential, now the limit for this sphere will be, a limit for this sphere will be to find the potential will be from, let's suppose where from infinity to this point at a distance of r, right? And we know the potential at infinity is by reference taken to be a zero, right? So we'll at infinity the potential will be zero, and at this point P at a distance of r, that there will be some potential. Let's call that as V. And we know that outside region, for outside region, the electric field for the sphere is nothing, that's kq, right? KQ over R. KQ over R square, right? That's the electric field due to sphere, right? Due to sphere outside the sphere, right? So we can just put in this value of electric field in this equation to calculate the potential for the outside region, right? So integral of dV will be V. So this will be V here, right? Minus integral of KQ upon R square dr with the limits infinity to R, right? Infinity to R. So minus KQ will be here, right? It will be outside integral, and integral of dr over R square with the limits infinity to R, right? That will be equal to minus KQ. Integral of dr upon R square will be nothing. That's 1 by R square. It will be equal to minus 1 upon R, right? With the limits infinity to R, right? So it will be KQ. Now putting the limits, upper limit minus lower limit, that will be 1 upon R minus 1 upon infinity, right? And 1 upon infinity is 0. So we get the potential as KQ over R. So it means that for a conducting non-conducting sphere, or even if there is a conducting sphere, the potential outside the sphere will be same as that of a point charge at a distance of R, right? So that's KQ over R, right? So KQ over R will be the potential for the outside region, right? So this is the final potential for V outside. V outside will be equal to KQ over R. So this will be the potential due to this solid non-conducting sphere for a point which is outside the sphere, right? Now let's move on to the calculation of electrostatic potential for this sphere, but for the points which are inside the sphere, right? It means that R has to be less than or equal to capital R, right? Now we'll be using again the same concept, right? We'll be finding the potential. We'll be integrating the same potential equation, right, with the proper limits to calculate the potential inside the sphere, right? Provided we know the electric field inside the region of the sphere, right? Let's suppose that we know dV will be equal to minus ADR, right? Minus ADR, or we can write it as integral of dV, that will be equal to minus integral of ADR, right? ADR. Now this point P lies inside the sphere, right? At some distance, this point lies inside the sphere, right? At some distance small r, right? So R is less than capital R, right? So it means that now once again we'll be integrating it with infinity to R, right? But now in this region the electrostatic field will be different, right? Or we can split this integral into two different integrals, right? So integral dV will be once again V, right? So we can write it here as minus integral of infinity to capital R, right? ADR, and then we'll integrate it from capital R to small r, from capital R to small r ADR, right? So here between the limits infinity to capital R here is the point on the surface of the sphere, right? The electrostatic field has to be equal to KQ over R square, right? KQ over R square. But for inside points, the electrostatic field is different. That's equal to KQ small r upon R cube. So this is the electrostatic field for inside region, and this is the electrostatic field for outside region. Now let's plug in these values of electrostatic field in this equation to calculate the potential in the inside region, right? So V will be equal to minus integral of infinity to capital R E is equal to KQ over R square, right? The limits, right? Now from limit capital R to small r with the value of electric field as KQR upon R cube, that's dr, right? Now once again minus KQ, integral of dr upon integral of 1 upon R square will be minus 1 upon R with the limits here in this case infinity to capital R, right? So we'll be left here with KQ over R cube, right? And the integral of R dr will be R square upon 2. So we'll write 2 here, R square with the limits capital R to small r, right? Now substituting the value of limits here, minus it will be plus kq upon r, right? So 1 upon infinity will be 0 here. That term will vanish. We'll be left with plus kq upon r only here. So it will be minus kq over 2r cube, right? 2r cube with the limits r square minus r square, capital R square, right? So this will be the final potential, right? That's kq over r minus kq over 2r cube multiplied by r square minus capital R square. So this will be the final potential for the inside region at any point r, right? At a distance of r from the center of this sphere, right? Let's discuss the variation of potential with r for this case, right? The variation of potential r for this case. You can see that for outside region, the potential was equal to kq upon r, or we can say that for outside region, the potential is inversely proportional to 1 by r, right? That's inversely proportional to 1 by r. But this is valid only for region r greater than r, right? Or r equal to or greater than r, right? And for the inside region, you can see that this is how the potential is varying, right? How the potential is varying. It's varying as r square, right? So we can say that inside the region, the potential will be varying like this. So that's, we'll plot the V versus R here, right? So this is how the potential is going to vary for this case, right? So this is how the potential varies. So at as R tends to infinity, right? The potential will tend to 0, right? And at this point here, the potential will be maximum, right? So it will be continuously decreasing, right? So this is how the potential will be varying with the distance r. This is for the solid sphere only, right? And for in case of hollow sphere, the potential inside region is a constant, right? For inside region, the potential is a constant, right? And outside region, the potential varies as. So this is how the potential varies for a hollow sphere, right? So that's how how the potential varies at a distance of r. So let's discuss about the question here. The question is, a non-conducting uniformly charged sphere of radius r has charge q. Find potential at distance of 2r and at a distance of 3 by 2r, right? So we can see that for both the distances at a distance 2r and 3 by 2r from the center. So it means that both the points will be outside the sphere, right? So we'll be using the formula for calculating the potential outside the sphere, right? So the potential outside the sphere is nothing. That's the same as that of the point charge, right? That's kq over r. So it means for part A, the potential will be equal to kq over 2r, and for part B, the potential will be equal to kq over 3 upon 2r, right? So we can write it as 2kq over 3r. Now let's suppose for the third case, let's suppose at a distance r is equal to r by 2, means inside the sphere, right? You have to calculate the potential. Then what you will be doing is that you will be applying the formula for the potential for inside the sphere, right? And you will be able to calculate the potential inside the sphere, right? So we have another question here. The question here is in which region electric field is maximum, right? We have been given a potential versus position graph here, and there are 4 graphs here, right, with different slopes: region 1, region 2, region 3, and region 4, right? Region 1, region 2, region 3, and region 4, right? For region 1, you can see that potential is a constant potential throughout till the region 1, till the region 2, and then for all the 3 regions, R2, R3, and R4, the slope of potential and x is different, right? So we know that potential electric field is nothing, it's minus dV over dx for electric field along x direction, right? So it means dV over dx is nothing, is the slope of potential and x, right? Slope, it represents the slope for potential versus x graph, right? So for region 1, we can see that the potential is a constant till region 2. It means there will be no electric field, or for region 1, the electric field will be 0, right? Electric field will be 0 because slope is 0, right? For the region 2, region 3, region 4, also for region 4 also electric field will be 0, right? Because there is no slope at all. And for region 2 and region 3 only there is some slope. And we can see that for region 2nd and region 3rd, in case of region 2, the slope here is more. It's more steep. Slope is more than region 3, right? So slope of R2 is greater than the slope of R3. So it means that the strength of the electric field will be more in region 2nd, right, than region 3rd. So it means that E2 will be greater than E3, right? The electric field will be maximum in region 2nd. In region 2nd, the electric field will be maximum, right? So that's it for today. In the next class, we'll be discussing about the capacitors, right? So we are finished with the potentials due to all the types of miscellaneous problems, right? We have done the potentials due to hollow sphere as well, and potential due to non-conducting sphere has been done. Now in the next class, we'll be using all these potentials, the concept of potentials, to calculate the capacitances of different capacitors, right? So that's it. We'll be meeting in the next class. Take care and goodbye.